Welcome to HotChips 2024. Tutorial 1. AI-assisted hardware design.
Okay, welcome back. This is Hanxian Huang. I'm a final year PhD student from University of California, San Diego, and I'm working with Professor Jishen Zhao. So my research focus is more on leverage the machine learning to optimize for software system development. And recently, we are also trying to leverage what we have from AI for software to also help AI-assisted hardware design. And today, I will talk about domain adaptive LLM for chip design. Basically, Stelio and Hans and Mark show their techniques and examples more from industry perspective, and I think I will show like what people are more interested in academia. So this is what I have today. So first of all, I will talk about like a little bit on the motivation why we want to do a domain adaptive LLMs, and then go over some of the domain adaptive LLM techniques. And later on, I will focus more on the examples for domain adaptive large language models for chip design tasks. So first of all, why domain adaptive LLMs? So Hans also showed the history of the LLMs, and as the model size is going bigger and bigger, so large language models has extensive knowledge and also the capabilities to do a lot of tasks and already achieve a lot of success in different domains. So basically, it can do natural language understanding and generation. It's good at reasoning and problem solving, instruction following, code generation, and even multimodality. So we want to make the best of this existing knowledge that already encoded in today's pre-trained foundation models. And on the other hand, since these models are more for the general purpose, so they might lack of the specialized knowledge that specific, for example, for the chip design domain. So here I categorize the domain adaptive LLM techniques in the different stage where we can adopt this domain adaptation in model training stage, model fine-tuning stage, and model inference stage. So in the different stage, we can kind of have different integration depths of the domain knowledge, and also like different stage that have different requirement of the training or fine-tuning cost, also your resource, and also your accessibility to the domain data. So first of all, let me, so since Hans already introduced a lot about the detailed techniques of the transformer model, what are they and how they are used, and also some key concepts on like the autoregressive pre-training. So here I mainly will compare like the differences of the domain adaptation across different stage, like training, fine-tuning, and inferences. So basically in the model training stage, so you can either like do training from scratch, or you can train existing general purpose foundation model, but integrate your more domain adaptive data set. So given the base LLM, and what you need to do is you really need to collect huge size of the domain data, and then you can get your domain adaptation pre-trained foundation model. And so for the pre-training stage will require more resource and data, but it will give you like better foundation model that have deep understanding on the domain, on the like chip design domain. But if you have like less resource or like less data, or you for the best cases, if you have like task specific data sets, you can just do fine tuning. So fine tuning, you can like either like fine tune the many parts of the pre-trained model, or you just train the adapter to like make it attune that part to make it do a better job on your specific task. And this one will like kind of a trade-off. So you will use less resource, and you will require to collect less data sets. But it also made the best of the pre-trained knowledge of the foundation model and adapt it to your specific task. And the third one is the model inference stage. So I think this is the most accessible way or most easier way that people may want to try when they want to adopt LLMs for some domain-specific task. So in the inference stage, what I will cover here is the like prompt engineering techniques, especially the in-context learning and chain of thoughts. I will show some examples later. And also give a teaser on the agent. So I will only go over a simple example, and I think Mark will go over more of the agent. And then also show some example of the retrieval augment generation. So given all these like different stage and different techniques that you can perform to do the domain adaptation, so how can we choose the domain adaptive techniques? So basically, we want to consider, first of all, the model that you have access to, and also like to what extent that you can access to the foundation model parameter and the gradients, so you can it decides whether you can like tune the model or not. And the second thing is you need to consider like what kind of compute budgets and resource that you have. And the third thing is you might have some specific task in mind, and also you need to consider like the amount of domain data that you have. And then later on, I will go through some techniques and examples in these three different stages. So let's start from the pre-training stage. So for the pre-training stage, what we can do for the domain adaptation is mainly the domain adaptive pre-training. So basically, you might have access to some general purpose foundation model that can generate like Q&A documentation or code generation. But those are more for the like pre-trained for the from the general corpus. So for the Q&A, it is mainly for the corpus of from English, and for the code generation is mainly from the corpus that from Python. So you might think of like how can we let the model to be aware of more on the natural language that related to chip design, and also the programming language that we use in the chip design. So the deepest integration of the domain knowledge is that we can do domain adaptive pre-training. So one example here is the chip Nemo. So to prepare for domain adaptive pre-training, we need to consider, first of all, what are the available foundation model that we have. For example, Llama 3. So with the accessing of the model parameters and gradient, you can do the you can tune the model based on your collected domain data set. And the second thing is you need to prepare a large domain data sets, and from two aspects is that for the hardware specific programming language parts, you can collect hardware-related code like RTL and also some test benches. And for the natural language perspective, you can collect like the hardware-specific described in the natural language, and also some documentations. With the foundation model and domain datasets, another important thing is the training resource. So taking ChipNemo as an example, so it leveraged the Llama 2 foundation model, and for sure it actually provides like different versions of different number of parameters, and then it adopt the domain adaptive pre-training on the 24 billion tokens of their collected data sets, and over thousands of GPU hours to get their domain pre-trained foundation model. And after you got those prepared for the domain adaptive pre-training. So how to perform this step? So one main thing that you can improve the model performance is that since the general model is more trained on the general purpose corpus, so one thing is that you can tune a domain adaptive tokenizer by to let your tokenizer to be aware of the more in-domain corpus. And for the model training stage, it can be pretty similar to what we have for the general foundation model pre-training. So basically the next token prediction. And I believe Hans already covered some of that in his tutorial. And after that, the outcome of the DApp is that we have we can obtain this domain adaptive foundation model, and also if you pre-train it in different versions of the foundation model, you can also have like different versions of foundation model with various number of parameters. And also this model can be further tuned to different chip design downstream tasks. So the second part will be the task-specific fine-tuning. So different from the pre-training part, this part is not for the domain itself, but more specific for some concrete task. So here I will cover 4 topics here: the foundation model and specific tasks in the chip design, and also the datasets and benchmark and metrics that we will use in the task-specific fine-tuning. So from the foundation model, so like 2 choices. You can either like access to some open source general purpose models. Here I list some of them. They are actually more for the code generation task. Or you can like do your own pre-training to get your pre-trained foundation model like ChipNemo. And for the downstream tasks, I think Mark already have the roadmap to show many of those tasks. And here I will more emphasize on and also show some examples later for Verilog script generation, verification, debugging, and also assistant chatbots. And then for the data set, so it's actually always a big problem that, especially for academia, that how can we collect the domain task data set. So some sources that we are widely considering, so for sure you can collect data from the internet. But one problem is you need to carefully to do data filtering and data augmentation to promise the data quality, and also to like take care of the IP and privacy issue. So one example is you can crowd a lot of existing Verilog code from GitHub open source repo. Also, you can collect them from tests. You can collect the examples and also the those descriptions from textbooks. So for sure, companies will might use their own proprietary data, and like if you don't have the large enough data set, we also will consider synthetic data. So you can either, actually I also have example for the synthetic data set. So you can either like collect it by human, or you can also ask like the novel large language model to help you to generate the data sets for chip design task. more thing I want to mention is you can also collect data from some context. So for example, there's a large language model for hardware design context from ICCAT this year. I think it's still open. So feel free to check the context and also like check the updated data set. Another thing that we need to do for the domain task dataset is that we need to label the dataset. So yeah, during the fine tuning, you need to inform the model that like whether it's doing great or bad after the model after the new iteration of the model. So you either need to label the dataset or you need to kind of provide some test benches or have some form of rewards to the model. So taking the example of the RTL script generation, the input will be the design description or some domain instructions. And then so how you inform your model is that you either can provide some reference code or you can provide the test benches so it can collect some test pass rates to fine-tune the model. And other examples, for example, for the hardware security will be you need to label the common vulnerability, vulnerability enumerations, also common weakness enumerations. So basically, you need to label those security issues in the code. And also for the debugging task, you may want to label the wrong and correct data pair. So after prepare for the data sets or after you fine-tune your model, another important thing is you need to kind of have some benchmark to evaluate how your model works. So here I will introduce two benchmarks. So the RTLM and the Verilog eval, they are more for the RTL code generation benchmarking. So the RTLM, it consists of 30 HDL design tasks. It also provides test benches for each of them and also provide the makefile so you can automatically run the benchmarking. And the right-hand side actually show the flow of how it eval your RTL code generation. So in the benchmark, it will provide the design description, the test bench, and also in the benchmark, it also provide the golden reference from the designer. Using this design description as input, you will come up with some kind of prompt to ask the LLM model, for example, ChatGPT or other coding models to generate the RTL code. And then the RTL code will be sent to 3 stages of the testing. The first one is the syntax checking. So basically, you will compile the code and see if there's any syntax errors in the generated code. The second part is the functionality checking. So here we will use the metric of a pass at k pass rate to show how it works for the syntax checking and the semantic checking. So the pass at k rate here basically means the probability that when the model generates n codes, given your prompt or given your task description, like any of the k generated code can pass the test. So it shows this kind of probability. And the third stage will be evaluate the quality of the quality of the generated code. So I think this one is not widely used yet. So what I observed from the paper that work on RTL code design, they actually care more about on the pass rates. And also since the task, actually I can show it here. So these are the simple task description of what we have in RTLM. So it basically includes some arithmetic and logic problems in the RTL generation domain. And since currently you can see from the description, the task is still kind of simple and from the textbook level. So actually we still in a very early stage that we want to improve the correctness or say the pass rate of both syntax and semantics for the RTL code generation. And later on, we will also consider the PPA for the quality of the generated code. Here I showed an example for the multi-pipe 4 bits. So you can see, so the underlying part is the high-level description say like, please implement the design of a 4 bits unsigned number of pipeline multiplier and also more concrete requirement for this. And then later on, it will follow by the module name, the input ports, and also the output ports and some specification for the parameters. So this is how the RTLM benchmark looks like. And also to be like a step further, we have Verilog eval. So this one is actually have a larger size compared to the RTLM. So it consists of 2 parts. One is the Verilog machine, and another one is Verilog human. So Verilog machine is basically the description that I show you. It's actually generated by the ChatGPT. Also, you need to like filter or select what are the valid description for the task. For the Verilog human, is more like the human designer to write their own description based on the task. So there are like 2 versions of them, and they are all for the tasks collected from the HDL Bits website. So more kind of like leak codes for the RTL Verilog, and so it has like 143 for the Verilog machine and 156 for 156 for the Verilog human. So it's like larger size compared to the RTLM, and similarly for the metric, we also care about the pass at K rates for both the semantic and syntax checking. And also some examples here for the Verilog machine and Verilog human. So you can see, actually, when you ask the ChatGPT to generate the task description for you, it can actually like detail in step by step. For example, what will be the input clock, what will be the input resets, what will be the outputs, what will be the module. So when it comes to the detailed description, like compare with the Verilog human, we can also find like a lot of existing work, they actually have higher pass rates on the Verilog machine compared to Verilog human. So it also shows that the quality of the task description or the quality of the prompts will also affect the generation results. So I will show an example here of how to conduct the task-specific fine-tuning. So for this one, for the RTL coder, the task is RTL code generation, and the foundation model, they use Mistral 7B and DeepSeek coder 6.7B. And for the data collection point, you can see the this flow. So basically, it use more help from the GPT. So if you take a look at the green arrow line in this flow, so first of all, so the goal is we want to collect the instruction and the golden code pair. But actually, collecting the source code is more easier, but how to pair them together will be harder. So what they do here is, given a lot of source codes, it also collect a pool of keywords and ask the GPT model to construct a task description consisting from the keyword from the pool, and then make them pair with the source code that they have. And then they also will have some checker to check whether the instructions are valid or not. After that, they collect 27K instruction and code pair to fine-tune their model. And here I show their fine-tuning flow. So after collect the fine-tuning data sets, and they use these 2 foundation model to perform the fine-tuning. So this part will be also similar to the general fine-tuning. But the key part here is we need to collect the very high quality pair data sets for the fine-tuning. Here I show two figures that actually come from Verilog Eval version 2. So I think it's just released last week and it's very updated. So I kind of want to give you a sense of where we are right now in the RTL code generation. So you can see from the figure that like most of the smaller size model that under 100 billion parameter, they can only achieve like 30 to 50% of the pass at 20 pass rate. So basically means when you generate a lot of candidates, like what's the probability that at least one generated code of the 20 code can pass the all the testing. And for the larger model that over 100 billion, for example, Llama 3.1, and also some closed source model like GPT-4, they can achieve higher accuracy, like above 60. But we want to note that like for the general purpose code generation, for example, for Python, we like a lot of model can already achieve over 90% of pass at one rate. So basically means we only pick one candidate from the generated code, and it can pass all the tests from the test bench. So we can see there is still a gap that between the general purpose like Python code generation between the hardware RTL Verilog code generation. So I think the thing behind here is that the RTL code generation is much more complex. It's not only ask the model to describe the functionality, but also it considers more timing, synchronization, and also the physical modeling behind it. So I think this will be a continuing topic, and yeah, I will be like open to discuss on this later. Yeah, for more examples, I will not go into the detail, but I will show you like there's already a lot of papers that work using the fine-tuning method to adapt the existing LLM for code generation tasks and also for debugging for other tasks in hardware security domain. And then I will go to the inference part. So for the inference, people will think of, okay, it's easy to directly use the model. But as the data that I showed just now, the quality of the prompts that you input the model will highly affect how the LLM works on the task. So one simple example here is we can use prompt engineering to use the chat model as an assistant to help you to do the chip design. For example, it can be your program pair or to make some suggestion or some decent code sketch, or it can be your robot dog, so you can ask it to, you can tell like how I'm thinking about this design, but it doesn't work. So how to use the assistant chatbot is, first of all, you need to have a chatbot model. So usually we will use instruction-tuned conversational models, for example, ChatGPT. And then there's a lot of tricks there here we can do to improve the prompt engineering and improve the generation quality. So the first thing is here is the role playing. So it's related to the system prompt. So we usually will tell the model, assume that now you are a hardware expert, then blah, 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 what are the requirements and what kind of task you are going to solve later. And another thing is to provide either positive and negative example. So we usually call it few shots in context learning. So providing, for example, golden example for other for example, for the code generation task, you can give several of the input-output example that what you are expecting the model can generate, and then later on you follow your new task description and ask the model to generate the new answer for the new task. And next one is to break down the complicated problem. So it's quite similar to like what we are solving. The human being solving the problem is to divide and conquer. So one thing here is widely used is to ask the model to do the planning before it really generate the real RTL code. And the next thing here is to specify constraints and also concrete output formats. For example, you can use the begin and end text to say only include the code between the begin and end text, and also don't output any other analysis. Another thing is chain of thought. So you can, we actually have a lot of example of this, is that if you ask the model to solve what kind of problem step by step, you can find it works better than just give it a simple problem description. And another thing is we can do multi-tool interaction. So I think Hans already also mentioned this a little bit in the agent, and Mark will give more example on it. So basically, when we ask the model to generate the code, we don't want to just give it to do it in one turn. We want to do it in the multi-turn interaction style. So you can either include the simulator and the feedbacks from compiler and simulator, and then you can prompt the LLM model again, ask it to do multi-turn generation. So here is an example of the assisting chatbot. So you can see, first of all, you can do the role playing. You ask the model, say, hey, please act as a professional Verilog designer, and try to understand the following description of the task. And then what is the module definition? What is the specification for the input and outputs? And then ask the model to do the self-planning first, and then generate the code based on the planning. So this is an example output. So you can see the lights. Pink part is that it actually really do some self-planning. Like if I want to design this 4-bit unsigned pipeline multiplier, what will be the step? And then in the orange parts, you can see like different detailed steps, like how to divide and conquer for this design task. And I didn't show the real generated code here, but basically, like for this design prompt engineering, you can like improve the inference ability and trigger the domain parts of the LLM model. And more example, I will not go into detail here. So a little bit teaser on the agents. Mark will give more example later. So basically, we want to do the feedback loop and self-correction to provide to perform a multi-turn generation and correction. So basically, you first have some initial prompts as shown in the last example. And then after you generate the code, you collect the output from the agent. And then you also collect the feedbacks from the simulator or the compiler, like what are the errors happened, where are the errors happens, and for example, for some specific inputs, what are the expected output, but what's the real output that you get from the LLM model. And then you can extract this feedback and then generate the prompt again based on the feedback, and then do this multi-turn generation. So also an example for this multi-turn self-correction. So a follow-up prompt can be like, can you like generate the task code, or based on the task code, can you walk through some of the examples based on the feedback from the compiler or the simulator? So this blue part is the test bench that it generated. So similar to the RTL code generation task, so the test bench generation is also a specific case of the code generation. So it can be error or buggy in the generated code. And then later on, it will conduct a step-by-step code walkthrough based on these input cases. So, for example, in different time steps, like what will be the intermediate states of different variables across these different time steps to do this step-by-step code walkthrough. And then later on, we can feedback the simulator and simulator results. Say, please review this feedback and please analyze what will be the possible reason that these errors trigger, and we'll consider especially the failure inputs. So then the model will generate a new step-by-step plan and also reasoning about the possible reason for like what will be why the error triggers. And then the right-hand side is the fully correct generated code of after this multi-turn interaction. So next thing I want to talk about is the RAG. So Hans already introduced some techniques about RAG. So it's very important to improve the LLM generation ability. So basically, it includes an external database that you can put a lot of the domain data in the database. So one example here is the RTL fixer. So this one we want to do the given the generated code or given code pieces, I want the model to debug for me. So for this one, it also used a similar feedback loop. But what I want to emphasize here is how it come up with this RAG. So first of all, in the offline stage, you can categorize various syntax error from some offline datasets, and then you can collect the human expert guidance. For example, you can ask some expert engineering to provide detailed explanation for those compiler logs. After that, you can build a dataset for both the compiler logs and the error code segments, and also the human analysis for these compiler logs. And here I also have an example of the compiler logs and also like how we can collect the human expert outputs that can assist the model to better understand the compiler logs. So I will not go into detail here. And after that, I want to show the result of the RAG. So you can see with or without RAG, there is a actually significant improvement when you involving this extra database that consisting of the compiler logs and their corresponding human explanation to help the model to understand like what those compiler logs means. Yeah, so to conclude my presentation, I want to talk a bit more on the future direction. So the first thing is that I want to borrow the idea or the techniques from adjacent domains. So for me, I actually work more on the LLM for software development and compiler and some other programming tasks. So I think there's a lot of similarities. For example, when you generate code for other general purpose programming language, or when you do a compiler optimization for other programming language versus when you do optimization or generation for the RTL code or even other optimization in the chip design. For sure, there's also some difference and more challenges in the chip design domain. So the first thing is how can we borrow the idea and also how to migrate them into the chip design domain. And the second thing is I want to call for more, especially the open source datasets and benchmarks. So currently, I think for the LLM adaptation for the new domain, the high quality datasets will definitely a bottleneck that when we want to do the adaptation and improve the results of LLM on chip to assist chip design task. So several things here is, I think the code, the data set collection process is still not fully automatic yet. We still need human in loop, especially the more insights from experts to label data at the current stage. And another thing is currently we still care more about the accuracy of the RTL code generation, for example, the pass rates that I mentioned, and how to further consider PPA to further to optimize the code or directly generate the optimized RTL code is also an interesting direction. And the third thing is how to make the best of multimodal data sets. So for most of the existing work, we only consider the text format and some of the code format. So we also have like data to represent the hardware specifications and also diagrams to represent the architecture. So how can we further leverage those table and diagrams or figures as a multimodality input to inform the LLMs? And the last thing I want to mention is the collaboration between academia and industry. So for my own perspective, in the academia, we actually work more on the theoretical parts and the more foundational topics, and we are seeking more novel algorithms or for some novel or prospective application. But in the industry, I think people more care about solving practical real-world problems. And actually, in the industry, people have more data and resource for this topic. So I think it will be compared to other like LLM for system design or software design. I think it's like it has greater needs to that academia and industry should collaborate together. Yeah, so that's that's it for my presentation. Yeah, so I will give it to Mark. So actually, I know Mark is not because we want to we will working on the tutorial together. It's actually because he and his team work on a lot of great work like ChipNemo, RTL Fixer, and also the Verilog eval that I also mentioned in my tutorial. So yeah, let's give it to Mark. Thank you. Yeah.
Okay, thank you. So good morning again. Actually, this time I'll talk about an even more exciting topic, which is LLM agent, than the first talk. I'm super excited about this agent methodology because I feel like it can release the full power of LLM for chip design. So Hanxian's talk and Han's talk have already mentioned some aspect of the agent. So here I'm going to give a very relatively more complete coverage for agent. As I mentioned in the introduction session, AI can provide design assistance, right, in know-how, code generation, and task automation. I think agent will just enhance that capability way beyond just a baseline LLM model. So let's look at the agent performance on Verilog eval benchmark that Hanxian just mentioned. The Verilog coder agent that we just released is a sophisticated agent that can achieve significant better results than a non-agentic approach. As we can see, on GPT-4 Turbo, the Verilog coder can achieve 94.2% pass rate, almost solving all the problems in this benchmark. It is significantly higher than the non-agent GPT-4 Turbo pass rate, right, which is already the state-of-art results on Verilog eval, 60%. So, and other fine-tuned LLM models seldom exceed this number. The additional solved questions are reasonably complex, like including like state machine, tunnel map, like waveform, and some even application level RTL coding. So it is really, some of these problems are not straightforward for human to solve either, and yet the agent can solve it. And even using a Llama 3 as base model, Verilog code agent is also significantly better than the non-agentic approach. This shows the robustness of its agentic approach. So in the rest of the talk, I will first introduce some key concept of agent. Then I will introduce several use cases of agent in chip design. So let's first illustrate some key concept. First, for comparison, let's show the non-agent way as well, right? So in non-agent way, given a question, usually a simple one, the LLM will directly provide an answer. However, if the question is complex enough, that cannot be solved by simply calling LLM directly, then what do we do, right? So how do humans solve complex problems? We do problem decomposition, right? Problem decomposition. So we solve a problem step by step. And this step-by-step problem solving is called planning in the agent terminology. So because now agent will run many steps, we need to keep the stateful information, right? Just like hardware state, right? Stateful information from each step. Also, we need the agent to remember what's going on, right? So that means we need the agent to have a memory. And in order to solve even harder problem, we need to leverage tools, such as for computation tools or tools that interact with the environment. Therefore, agent has 3 key components: planning, memory, and tools. And we rely on LLM as the core engine to hook them together. So this is a basic framework for a single agent. Now, we can actually connect multiple agents together to form multi-agent system. And each agent play a different role, solving different part of the problem, right? And this is another form of a problem decomposition. Simply by the role, like each agent is focused on one particular side of the problem. So let's look at each component one by one. The first component is planning. This is probably the most important component of the agent. There are 2 ways to do planning, either with feedback or without feedback. So chain of thought planning or tree of thought plannings are without feedback, while react and self-reflection are with feedback. I'll study them in detail. Chain of thought is a very commonly used planning method. It plans all the steps in one shot, and it will generate the entire plan, all the steps, through its own reasoning about the task decomposition. And there are 3 ways to do this chain of thoughts. You could either give explicit instructions to the agent, such as, let's say we'll design a RISC-V processor. We should first do architectural design, then we do function specifications, and then we implement these functions in one at a time. This is explicit instructions. Or we can do implicit instruction, where we just tell the agent, go think step by step, and hopefully the agent can come up with a plan that can realize that task. Or we can have a demonstrative examples, where instead of asking it to design RISC-V, let's give examples of how to design Spark. And then with that example, the agent might be able to plan for the RISC-V. So one-shot plan have a difficulty to plan for very complicated task, because we often need to adjust the plan on the way. Therefore, there's a different planning method called the tree of thought. Can make plan one step at a time. And at each step, it make LLM propose several potential next steps. Then it evaluate each to find the best step to execute. So this planning step is like a search in a tree structure, which is why it's called a tree of thoughts. Because it's like a tree, you can also apply other commonly used search algorithms, such as breadth-first search or depth-first search in this manner. In addition, people also extended this kind of tree structure into a real graph, so you can make an even complicated plan. Now, as Hans mentioned before, LLM often hallucinate. So it's not good at some tasks, such as calculation as well. And sometimes we need it to access the latest data from the user. Therefore, planning without feedback would be very difficult in those situations. And that's why we would like the agent to talk to the environment, right? So to perform these calculations or retrieve the latest data, as well as the ground truth. So this React platform is a very commonly used method for planning with feedback. At each step, it will reason about its current state and generate actions to interact with the environment. And the environment will respond with the observations after this action. And the agent will then go iteratively, step by step, to continue interact with the agent. Sorry, continue interact with the environment. And this is one of the most commonly used planning methods in the agent. And we'll show its use case in our examples. Now, the React feedback is only from environment. It is kind of reactive, right? That's the name React means. So it does not fully leverage agent's memory capabilities. Self-reflection allows the agent to learn feedback from accumulated experience from the memory. So what is accumulated experience? They are like conversational histories of previous agent prompt and interactions with environment. The self-reflection method can reanalyze this conversational history and come up with rules to improve the next experiment. And these rules will be saved in the long-term experience memory for the agent to use in the future. Now, let's switch gears to talk about another key component, which is memory. Memory is needed to help agent to remember its state, as well as to store experience, such as for self-reflection we just mentioned. We want to briefly introduce some key attributes of memory. First, how memory is implemented. It can be implemented as in context, which means you just put the previous histories in the context of the next language model call. However, if you do that, you quickly encounter the context limit issue for the model. So you can save all your history into external file. You can call it archive your history. Then the problem is how do you retrieve from your archive? That's why a lot of implementation depend on external vector database. Then you can use the RAG methods to retrieve from the vector database of the useful information for the next agent talk. In addition, you can use structural memories, such as knowledge graph, to represent knowledges or informations that can be used by the agent. And with the knowledge graph, you can actually search through that. Now, second, what is the scope of memory? It could be a local type of memory that only used by a single agent. It could be global memory that can be used by all the agents, shared among all the agents in the system. It could be short-term memory, which only remembers the previous 3 conversations, or it can be long-term memory that remembers everything that happens. And finally, what's the operation that memory should support? Obviously, it should support the read and write. But in addition to that, since we have language model, it can also support some sort of reflection on the memory. Now, the next component is tool, which is very important because LLM is not good at many things. For example, math. And also LLM cannot interact with the external environment. They need the tools to interact with those environments. And it turns out modern LLM have been trained to call tools when necessary. if we actually specify the tools in terms of a JSON file, right, the format, how do you call this tool, the inputs, the outputs, the description of the function, then LLM is able to reason about your request and generate the function calls. So the procedure of doing function calls is like this. So in the beginning, the application will just send the prompt as well as the definition of the tool to the LLM. For example, if the prompt wants to calculate a multiplication, then tools is a calculator, and the description is calculate a math equation, and input is a string, output is string. Then the LLM can return with the function call specifications. Then the application will execute the tool and then return the results back to the LLM, and the LLM can then send the final results back to the application. Now, previously we discussed planning, memory, and tools, which are like key components of a single agent. Here, we want to connect agents together to form multi-agent system. For example, we can connect them and let them conversation with each other, let them talk to each other. So LLM is trained with conversational skills. That's why you can create a chatbot with LLM. So they are super good at conversations. Therefore, once you connect the input of a LLM to the output of another LLM, right, and vice versa, they can do free-form conversations. And here's the example of what kind of free-form we can generate. And I would say this is an implicit task decomposition, because we only ask each agent to behave like in a specific role, and they will automatically accomplish the entire task collaboratively. When there are more than two agents, right, usually there is a chat manager to direct the conversational traffic. And the chat manager should be aware of the roles of each agent. And it will take turns to talk to each agent. It has to use its own intelligence to decide which agent it should talk to. And it can also use some predefined algorithms, such as like round robin kind of, to select the agent. So in addition to just agents talk to each other, that seems to be kind of very casual. When we have specific plans for the agent to execute, we can connect the agent according to this sort of predefined task flow. For example, in software development, there are designing phase, there are coding phase, testing phase, that you need to accomplish these three phases in sequence. So you can form a task flow to allow multiple agents to work in this sequence. This is a form of explicit task decomposition. And unlike previous multi-agent system, which only has agents just talk to each other, right, without explicit task definitions. And you can even combine these two methods together, as shown in this example. There are like two agent conversations to accomplish each subtask in a task flow. For example, in this design phase, there is a CEO, right? It talks to CTO to form the plan, the design plan. Right? So the high level, it's a task flow, well-specified task decomposition. Low level, you have multi-agent just chatting to each other to accomplish that. This is also very commonly used methods in implementation agents. So let's look at the three examples. I will start from simpler ones, gradually move to the complicated agent examples. This simple example is a timing report analysis agent. Basically, we want to design an agent to analyze timing report. This timing report includes information like which corner and which run, what time of the run, and the list of timing metrics like WNS, TNS, FEP, as well as slack distributions. And the goal of this analysis is to identify which timing run is better and provide high-level takeaways, as well as design QOR summaries, like the last 4 lines of report, right? So we'll show something like, oh, this particular run generates generally show improvements in TNS, and however, WNS degrade, and the slack distribution show improvement in all corners, but in particular corner it suffers some problem. So this sort of high-level descriptions we want to analyze. So because LLM is not good at math, we need to build some tools to help it. And the tools here includes like timing metric calculation tool, right? Let's calculate the change on one of the timing metrics. It also includes another tool to calculate the slack distributions, which will report between 2 different runs what's the slack distribution change. And for planning, we use a simple chain of thoughts as well as the React agent. The chain of thoughts instruct the LLM to first analyze the change of WNS and TNS, and second, compare FEP, and third, compare slack distribution, right? And finally, summarize based on certain aspects, right? And I explicitly tell the LLM that don't compute it by yourself. Use the provided tool. Then we use the React framework, right, to call the given tools based on this chain of thoughts instruction. Note that although we are doing both, right? We're doing both chain of thought and React, right? They can combine together. There's no problem. Chain of thought is just a prompt. React is additional prompt, right? So they can combine either way you want. Now the second use case is a different use case. And it's like special because it actually tries to leverage LLM for optimization of some designs. So here we basically ask LLM to assist in finding optimal device clusters for the standard cell layout. A cell layout generator often leverages the cluster constraints to optimize the layout. And different cluster definition can result in basically different layout. And some cluster definitions have better layout generated. Now, compared to the previous use case, it certainly requires a lot more domain knowledge for LLM to do a good job, right? Because now it's actually manipulating the design. So we need to have a very extensive knowledge extraction step in the agent flow. So here, the knowledge that helps the agent to optimize clusters, including the netlist topology, the physical layout of previous clusters, the routability results. All this information will be provided to the agent as context. For example, there's important problematic nets has to be identified. And from this knowledge, the agent then will use a regular React flow to call custom tools to accomplish the task. And these custom tools including analysis kind of tool and the memory-related tool. The analysis tool will compute the cluster scores, which is given a feedback to the agent. It also includes tools for netlist analysis for agents to locate potential useful clusters. Memory-related tool include tools to save a cluster proposal, as well as the tools to retrieve the best proposed cluster having found. And this agent actually achieved pretty good results on our libraries. So here's an example of how agents leveraging domain knowledge and tools to perform the optimization. Let's see if we have time. So first, the domain knowledge will inform the agent that a particular net is important. And the agent think, okay, you should call a tool to analyze this net and its connected device. Then the tool will return the new clustering score. And then the agent will decide whether to save it or not. And it's interesting to see that the agent is able to reason through this task given only limited instruction, right, on how to perform optimization. Finally, let's revisit the Verilog generation use case, which gives super good results on a Verilog eval benchmark. So compared to the previous 2 use cases, this is a more complicated one. It uses multi-agents. It uses the task flow. It extracts the custom knowledge graph and as well as the custom tools. So at high level, it has 2 stages. The first one is the planning stage, and second one is the implementation stage. The planning stage will generate plans with multiple tasks for code the implementation stage to implement. And the planning stage leverage a custom knowledge graph called TCRG, task-driven circuit relation graph, to generate a detailed task specification. And then the implementation stage leverages a tool called the AST-guided waveform debug to debug the mismatch of the code. So let's look at detail for each stage. So in planning stage, first, a two-agent system, they are doing chat, right, is used to generate task plan from specification. One agent is responsible for plan generation and another for verification. So they generate this plan step by step. However, this generated plan is usually not detailed enough for accurate code generation. So we need to add more specifics for this specification. This is accomplished by additional two agents. One, I think I'm missing some of the slide miss. Yeah, so this is accomplished by additional agents. So the first one will extract the relevant circuit information and build a TCRG graph, right? And the other one will relate the task that it needs to generate, as well as the graph, to extract the relevant nodes and add those information to the original plan. So now we have a more detailed plan. So this is a multi-agent system to figure out how to create the right plan for implementation. Once we have the plan, we have another two agents to generate the code. So one agent write code, the other agent fix the syntax error using open source Verilog simulators. And after you completed all this task step by step, that we have the final code. But the code could have a bug. So that's why we need to actually fix this bug. It's called a debug test. This debug agent will leverage React and a AST-based waveform tracing tool to identify the bug. And here's the detail. So when there's a bug, we know there's a final signal that mismatch from the golden signal. Then what do we do as a designer? We go look at the code and trace back the signal. So the AST tree tool just accomplishes the same thing. It traces through the signal back to the signals that defines the output. And it will do this level by level until the problem is fixed. And once we find the right signal, we'll append its trace to the context of the agent. So the agent can look at the trace and the error and decide what's the right code to fix. Okay, so I think I concluded the agent introduction. Here's some closing thoughts. So what kind of problem can be solved with agent today? I think there's a lot of assistant problems can be already solved by agent today, like design generation, debugging, review analysis, even optimization. The key is this task needs to be able to decompose into tasks with low to medium intellectual effort. Right? So if you can decompose your problem and each sub-problem is easy to solve, then you can use agent. This will significantly improve the agent's productivity and make designers' life easier. However, we do notice that extensive domain knowledge, domain capabilities is required to build useful agent for chip design. As in the previous use case, I have shown that the designer has to come up with the knowledge to guide the agent. This includes the hardware design knowledge, as well as how to use commercial, like EDA tools. So I think the key point is agent's capability really comes from the designer's insight and also specialized tool. So that's the key point, right? And that makes, like, when you want to teach your agent how to do things, you give your insight and you tell it how to use tools. So the final question is, can agent actually become intelligent enough to solve hard questions? I think it's yes. Because you think about how we scale, how people work together, right? In the beginning, it's like we don't use tools, right? Then we use tools as a human being, right? Then we use tools to become more powerful, and then there's multiple human work together, it becomes society, right? And we develop even more sophisticated tools. So I think the agent will behave, will evolve like that. So right now we are in the very early stage of agent. In the future, you can imagine there will be very specialized agents doing specialized design tasks using specialized tools, and agent can even create an agent on its own, like your agent creating agent, and then it will evolve into a very complete systems to solve our problems. And that's all for my talk. Thank you.
So thank you all for attending. We have a couple of minutes for questions, but first I want to thank these fabulous speakers. They just did an amazing job, I think, so I just want to recognize them one more time. This is an area that is just changing so fast, and having a tutorial on this was actually quite challenging because everything is changing at lightning speed here. But hopefully you got good insights from the talks and kind of know what questions to ask next. And as that's happening, we're assembling here on stage. Okay, well, we'll just go ahead and take a question from over there first. Your name and affiliation, please. And
Hi, this is Ramesh from Synopsys. I had a question on the domain adaptive fine-tuning. You using, say, the Llama 3 model as an example, you're basically doing pre-training and then just, say, task-specific, say, something like Python script fine-tuning, right? But then those same Llama models have a bunch of instruction tuning for Python coding and reasoning. Didn't we not lose all of that, or how do we bring that back? I mean, what's your take? I mean, did we, right? So, anyway, good.
Yes, thanks for the good question. So I think for the fine-tuning itself, we actually focus more on providing the task-specific inputs and outputs, golden pairs to let the model know about how to perform well on specific inputs and outputs. So I don't think that will hurt the instruction parts of the original training, but we'll more emphasize more on the new task that you are fine-tuning the model on. Yeah.
So you're saying you're not starting with a base model, you're starting with the instruction tune model and then doing further training, right? Is that?
Yeah, you will start with, so you will start with you can start with the general purpose Llama 3 model, and that has some general instruction pre-training, but you can also tune in for your own instruction and code generation parts. Yeah.
Okay, thanks.
Thank you.
okay, do we have? Okay, go ahead.
Hi,
I'm sorry. Can we? We'll do the Slack question, then we'll get to yours. Go ahead.
Yeah, so sort of a multi-part question from Cody Sisler, AMD, and Huang Ren, Meta. Do you feel that AI is in a good enough state to replace commercial tools, or should these be used more for design exploration? And how much of these Gen AI and LLM techniques are already deployed in production chip design flow? And are there phases in the design cycle where AI is not suitable?
Who wants to take that? Hans, go ahead.
Well, I think in a way we can rephrase the question like, is generative AI ready to use tools? So in other words, are LLMs or agents able to use EDA tools like a human being does in order to get the best solution ultimately down the line? I think we're getting there. I mean, generative AI, LLMs, they make mistakes like human beings, and we need to learn, and we need to maybe adapt to the new paradigm. We need to learn how to work with software that makes mistakes. I mean, we're not used to that. It's brand new, right? And I think it'll take time for us as designers to adapt to this new way of working and getting the AI to assist us, literally, getting the best results.
Yeah, I would agree with that. We got a few new toys in the last couple of years, right? And they're very, very cool. But it doesn't mean that our older toys go away, right? I think Mark's example of the calculator was great. Like, imagine if we said, we're not going to use calculators. We are going to train an LLM on doing any possible addition and subtraction out there, which would not be a very efficient way of doing things. So we have now proven algorithms to do a lot of great things from, for example, think about routing, think about timing analysis, think about optimizing placement for local density. They are very good mathematical solutions to these problems. The orchestration, however, opens up new opportunities, and I think that's what we've seen in today's talk, be it big agentic frameworks or otherwise, to use these toys in a different way, make them more adaptive to unknown environments. And I think that's where the opportunity lies going forward.
Okay, great. Question over here.
Hi, Anastasia from Anastasia in Tech. My question is to Stelios from Synopsys. So I used to be a heavy user of Synopsys tools for the physical implementation and sign-off. So your presentation was very, very insightful. Thank you very much. So I wanted to ask a question. What is the rate of adoption of AI tools in the actual flow now? So has companies already started to rely on these tools for the production, so for the real tape-outs?
Yeah, I think that's a great question. So I call it the first wave. If LLMs, or I should say natural language-based assistance is the second wave, then RL-driven optimization is certainly the first wave. We saw commercial tools become available as early as 2020. And now, where we stand today, without having the benefit of the latest statistics, but what I've seen is we're well past the 1,000 or more as an industry, commercial, not test chips or proof of concept vehicles, commercial tape-outs with these kinds of tools. And that works in two dimensions, right? One is to take applications like physical optimization and grow the footprint, meaning add more capability, more search spaces, dig deeper into the domain. The other dimension is adding more domains. So verification, for example, is a domain where we've paid a lot of attention in the last year and a half. And now we see, analog circuit optimization. We see test. So that's another domain. I think we are well past the mainstream adoption milestone as an industry at this point in time.
Thank you very much.
Absolutely.
Okay. I'll take a question from over there.
Yeah, thanks for the talks. These are great. Amir, I did my PhD in UC Berkeley and currently starting a company in the AI for chip design. A question on the Synopsys talk, maybe two questions. You mentioned that there's limited training data, and that's why we use reinforcement learning. At the same time, reinforcement learning requires almost the same amount of data because you have a neural network you have to train, and I'm assuming you're using a neural network to train that. That's one. And two, one of the problems with reinforcement learning is that it's very stochastic and not stable. So it's not reproducible. Like you can run the same run twice and get different results. Versus an industry that is very risk averse and they don't want to take a risk and put $50 million chip on the line. So how do you handle the training? And then even when you handle the training, how do you make reinforcement learning reusable or something that can be deployed?
Thank you so much for the questions. I think very insightful questions. Let me start with the training. So the absence of data is a priori, meaning that if you put yourselves in our shoes, when we're building these kinds of capabilities, and we know that they're going to be used by hundreds or thousands of designers in different data environments, clearly we don't have that kind of data available to us. Right? Although we of course collaborate with a lot of companies and many of them in this room. So we have to use the data that it's available to then allow the system to generate enough data past deployment to be able to extend the models further and to make decisions that are applicable to that design environment. And so there's on one hand, it's challenging because we see reinforcement learning systems that like to generate a lot of data and to do very deep search trees, which are difficult to do. At the same time, there's also a benefit, meaning that if you were to look at all the different design styles out there, you have pockets of design that do not necessarily impact other pockets of design. So being able to run these tools in specific design environments with specific constraints, benefiting that specific design environment won't necessarily transfer very well to another design overall. So that kind of balance was actually something that we're able to hit, and that's how we're able to make the technology continue to learn and adapt post-deployment, right? Your second question is also very interesting, and it points to, I think, mostly the question of methodology. So at the very beginning of this, we did, of course, a lot of exploration and a lot of research, and other people did as well, right? At the very fundamental level, you could give an RL agent, some transistors and some wire and just go for it, right? It's the same thing as the calculator problem, right? Why would I use a computational technique that's based on search to solve problems that can be solved otherwise very, very efficiently, in fact, proven to not be able to be optimized any further than current solutions? So we backed away from the transistor and wire paradigm, and we said, what if we were to teach these agents how to use tools and flows? So now it doesn't need to actually solve local density optimization. It can rely on a tool that's been doing it for 30 years to solve these local linear problems while focusing on the higher level decision-making problems that are harder to do.
All right, thank you for your question. Yeah, probably have time for maybe one more here and one more here, and then we got to go to lunch. So go ahead.
Question from Perry Lee, HP. What's your perspective on the inference performance requirement for ML-enabled EDA tools? We know training is prohibitively expensive, and we also require LLMs to produce tokens faster than a human can read, like less than 100 milliseconds per token. So what would be a similar requirement for ML-enabled EDA tools?
Can I? Yes, so I think if you look at the inference compute requirements for LLMs, there's not going to be that much of a problem. I mean, training, yes, requires, very significant resources, but that's a one-time effort, and there is, multi-user worldwide benefit. But on the inference side, the compute power in itself is already much less. And also, as we're building specialist agents, you will get models which become specialist model in a certain domain, and they often need to not be as big as the ChatGPT 4.0. So in other words, with techniques like transfer learning, we can teach much smaller, dedicated models to do the job specifically what we want them to do within a certain domain. So ultimately, when it comes to the discussion on power consumption concerns, like in Bitcoin world is a concern, right? I'm not so worried about inferencing using LLMs from a compute power perspective.
So I actually have like to add on to that. I think the inference for like AI, especially generative AI language models used in design tasks is actually very, very important. The reason is actually there's many reasons, right? So first, first and foremost, can you do reliable inference? Right? This is without reliable inference and efficient inference, right? You end up with like non-usable product. I think for chip design, many companies prefer to have the model or the data not leaving their print, right? So that means the companies has to build their own inference infrastructure instead of rely on public cloud. So that means there's a lot of work to get it done, have internal inference infrastructure. Basically, they need to build up their AI infrastructures, right? Just like it takes a long time for companies to build hardware infrastructures for EDA tools, right? So that's one problem. Another problem is the context limit, right, for language models. So especially in this agent framework, you will actually see that the inference workload become actually a lot. Like when we see some of our agent framework, you can see that there's the context can be very long. And even though it cannot exceed the context window of one particular LLM call, we actually need to run like hundreds of LLM calls, right? So, and it could be like thousands or even more when you have more agents, right? So that means there's a lot of cost associated with using this AI. And that points back to you need to efficient model, right? Smaller models that fine-tuned on our domain, as well as efficient inference infrastructures, quantizations, and things like that to reduce the cost. I think even right now, the cost is not that big. But given the time, especially if we want to use this on a daily basis on all the tasks, you can imagine, you probably need to build data centers to do this inference.
Okay, thanks, Mark. I think we may have time for one more quick question, but I don't want to make us get behind on lunch, and then the whole conference will be behind. So anyway, go ahead with your question, please.
I'm BJ from Harvard. I got a fundamental question, which is about what are you going to do, not about what needs to be done. What are you going to do, each one of you, for the open source ecosystem? Because every single example that's up there is an internal proprietary example, right? So what is it that we have to do in the open source ecosystem to enable things to move a bit more faster and more transparently?
I believe we strive to make most of our work open source, and that's why we actually created like multiple benchmarks that's open source, and we're doing dataset efforts with the community as well. So I'd encourage everybody to do the same, because compared to software community, we definitely lack of data sets and benchmarks. Yeah.
Anybody else?
Yeah, thanks, Vijay. Good to see you here. Yeah, so for me, from the academia aspects, for sure, I always hope there's more high quality and open source data set as well as benchmark. And for the specific like RTL code generation task, we are also trying to collect more, for example, from the open source lab projects to collect more practical and the problem that have higher complexity to improve the quality of the RTL code gen benchmark. Yeah, that's what we are doing right now.
Okay, yeah, from a Premise AI perspective, so we actually offer a free version of our tool, which is available online, really, helping, helping is not the right word, but, supporting open source and promoting the open source environment. We also, and I think that's an interesting perspective, as AI starts using tools, we can also use open source tools. So we're very much a believer of contributing to the open source infrastructure in order to, automate the open source tooling, next to, of course, the more closed source, if you will, tooling.
Okay. And yeah, I'm going to add the actually quite remarkable growth in capability, scale, and performance of open source models. So if you look at the role that these models are playing right now in identifying, perhaps some of those very targeted domains and task-based systems that you can find for code generation, verification, environment generation, analysis, these are the kinds of capabilities that enable us to build solutions and combine them with our own data sets so that we can build solutions that can be deployable into customer environments, whether those environments are on cloud or on-prem, to provide that level of capability. So giving the actual use, incorporation, and improve the performance of these open source models have been incredibly enabling for our own research and also going forward for our own products. It also comes with its own problems. We should also mention that, right? So you cannot promote an open source ecosystem without solving the problems of governance, for example, right? And responsible use. And that's where we also see upcoming regulation at multiple levels, including government, that will shape the evolution of both commercial and open source models going forward. So multidimensional environment with many, many different kinds of aspects that you have to look into it.
It's a very thought-provoking question. Fortunately, we're out of time, but the panel's available to discuss over lunch and for the rest of the conference. So I just want to thank them one more time. I think they did a fantastic job.